So hi everyone. Here we are going to learn about particle physics. Okay, and let us know the particles broadly. Although we all know that each and everything, whatever we have, they have the dual nature. That is wave particle duality. But as of now, let us focus on particles only. For the wave thing, we will have photon. So let us have a broader classification. Particles are either leptons or hadrons. And hadrons are divided into two parts, that are baryons and mesons. And baryons are further divided as nucleons and hyperons. So this is the basic classification which we will learn. And our goal is to learn about classification, then quantum numbers, which specify those classifications and what are the conservation laws. And then at final we will learn about the quark model, which applies to hadrons. Okay, the spelling is wrong here. So this is what we are going to do. So let us move forward. So as I have told you that particles are either leptons or hadrons, and each particle will have their anti-particles as well. So for example, I say we have electron, then it will have its anti-particle positron as well. Okay. So let us have a basic classification, and it is not only basic, but I feel it is complete. Let us learn it. So the first we will learn about leptons. So in leptons, you will find six leptons and six anti-leptons. So the first three leptons are quite easy. You just need to remember this one. The first three leptons you can remember with a mnemonic EMT or electromagnetic theory, whatever you can call it is mnemonic. Okay, there is no relation with the real electromagnetic theory. So E stands for electron, M stands for muon, and T stands for tau. Okay. So this is electron, mu1 and tau, and notice that the charge is indicated in the upper right side corner. That is, this is charge minus, minus, and minus. So they all have charge of -1 proton unit. Now, what the theory goes like, for each electron, mu1 and tau, you will have its neutrino counterpart. Okay, so we call it electron neutrino, muon neutrino, and tau neutrino. These are three counterparts. Now, so total till now we have six leptons, and for each lepton we will have anti-leptons as well. So for electron you have positron. For muon you have this mu plus. For tau minus you will have this tau plus. And simply you will have for each kind of neutrino you will have anti-neutrino. So if this nu is neutrino, then we put a bar to indicate anti-neutrino. So that is it. Now, hadrons are simply mesons or baryons, and baryons are divided into nucleons and hyperons. And we are also classifying hadrons into a new kind of classification on the model of quarks, but we will do it in last. First, let us follow this kind of classification. So, mesons, let us know that these all are kind of bosons. That means their spin is nh bar, and n is the integer including 0. Okay, so there are three kind of mesons. That is, first is pi meson, or we also called it pion. Okay, then there is k meson or kaon, and then there is eta meson. Okay, and it is exist in uncharged state, so we have no such classification for eta meson like we have for pi meson and k meson. Okay, so these all are these things, and we know that these pions are actually the uh, actually introduced in very early days when Yukawa was trying to explain nuclear forces. Okay, so these were mesons. Now let us look at baryons. So these all are in the classification of fermions that have half integral, odd half integral, unit of spin. Okay, so this is the formula. Now, nucleons are basically proton, neutrons, and their antiparticles. That's it. Now let us come to hyperons. Hyperons, this is lambda hyperon, this is sigma hyperon, this is chi hyperon, and this is omega hyperon. And let me tell you, this is not A, this is written wrongly here. This is the sign. Okay, this is called lambda hyperon. Okay, this is capital lambda. A small lambda is like this. Capital lambda is like this. So now we have done with the classification of the particles. Now let us know what quantum numbers are there. Just briefly, in detail, we will do it later on. But let us know right now. So we have total broadly 9 kind of quantum number. Okay, spin, charge, parity, lepton number. For each lepton, there is a lepton number. For each baryon, there is baryon number. Then there is isospin, and then there is strangeness. That is nucleons and hyperons are different. So they found that hyperons are something which is like acting in a strange way. So a strange way means they are forming through a strong interaction, and then they're decaying through a weak interaction. So there is some kind of strangeness, not only limited to this, but something more than that as well. We will see in the later on classes. Okay, so that is why they coined the new quantum number strangeness. And then Gell-Mann, this is my scheme, there is something like that. Then hypercharge as well, and hypercharge is also then classified in the form of charm, bottom or top. So these are the broader classification, these are the kind of quantum numbers. Okay, what exactly are they, we will look it in some time. And then each kind of decay or production, each kind of decay of the particles or production of the particle, whatever happens, they must follow the conservation laws. But we have simply here around total 11 conservation laws, okay, to quantify, but not all of them are compulsory to each kind of decay or production. Okay, like some are applicable only to weak interaction, and then others are applicable to a strong and electromagnetic interaction. So we'll see it, but right now we are just getting ourselves a brief introduction. So we have conservation of charge, lepton number, baryon number, isospin, and the component of isospin which we call I3. Okay, then hypercharge, parity, okay, and then charge conjugation parity, time reversal symmetry, CPT theorem, and permutation symmetry in spin statistics. So these all are the things, and they are simple in nature for our cause. Whatever UPSC is asking, it is not asking much. The only thing is these things are slightly complex. But complexity doesn't mean they are tough. Okay. They are definitely not tough, but they could be classified as complex. So now let us move into the real game. So let us briefly introduce ourselves again. Particles are either leptons or hadrons, and hadrons are two. First one is baryon, second one is mesons. Okay, or whatever you call first or second, that kind of classification is not required. And baryons are for the nucleons and hyperons. We have seen them all. Okay, so we are studying this. So let us study leptons in detail. So leptons have a spin half h bar, and we know that we have 6 leptons and 6 anti-leptons. So 6 leptons are simply electron, muon, tau, and then their neutrino counterpart. That is electron neutrino, muon neutrino, and tau neutrino. These are 6 leptons, and then for each particle we know that anti-particle exists as well. So we have this E plus, that is we call positron, then mu plus, tau plus, and then the electron antineutrino, muon antineutrino, and then tau antineutrino. So you must need to identify and read them. This is tau, and this bar means anti, and this mu is neutrino. That's it. Now let us know about details of leptons. The first one is for electron. This is for electrons. So how do they form, or how do they annihilate, or something like that? So what you take a neutron, and when neutron converts into proton, so one electron will form, and then electron antineutrino will form. Okay, and you will find a kind of pattern there. So it is not hard to remember. Let me tell you how. So we all know that neutrons are neutral, so they have charge 0, but proton have charge 1. Okay, so to balance it out, we can't have E plus. Okay, we will have E minus only. Okay, and whenever you have something E minus, you will always have anti neutrino. Okay, and how could you remember that? If minus is here, this, then the same bar will come like this. So that is a kind of mnemonic. Okay, this is not some kind of theory here, but we, for our sake of being handy, we could always try to have some mnemonic. Okay, and now let me tell you uh, the sign that each antineutrino is neutral. Okay, each neutrino particle or antineutrino particle, they are all neutral, so they don't have charges on them. So just know that. So let us come back and let me tell you once again. Look, when I tell you that whatever charges, so electron have charge, muon have charge, and tau have charge negative. And if they have negative charge, then there will be something with the positive charges as well, because we have a theory that for each particle there will be antiparticle as well. So these are nothing but antiparticles. But for neutrino, like electron neutrino, muon neutrino, and tau neutrino, they are neutral. Okay, so these are also neutral. That is it. So we have seen that neutron is converting into proton by giving one electron, E minus, and then electron antineutrino. Now let us come to proton. So proton have charge 1 here. Okay. Then obviously it is forming neutron with charge 0. Then to balance the charge of the left side and right side, electron this time will have positive charge. And if you have positive charge, then this sign won't be here now. Okay. That means you have neutrino and not antineutrino. So let me tell you, this is anti-neutrino, and this is simply neutrino. Now, if you have energy, then you can also pair production, sufficient energy, which accounts minimum value corresponding to the rest mass energy. So for electron or positron, rest mass energy is 0.511 MeV. So minimum you need to have a kind of photon energy, minimum double of that, to have one electron and one positron. And only electron cannot be produced, because that will violate the charge conservation theorem. Charges must be balanced. Okay, so plus charge here and minus charge here is overall making them neutral. And again, opposite of pair production is pair annihilation, which we can see here. Electron with positive charge and with negative charge, they are combining and they are annihilating, and only energy is being released. So this gamma is nothing but energy, photonic energy. That is it. Now let us have about muon. The charge is -1. It is unstable. Let me tell you, electron was stable, but it is unstable. And even tau lepton is unstable. Okay. So these are the some ways to make muon. So let us learn that how muon is forming. And these all things will help you to do one thing. That first you will learn that how charges are being conserved, and how neutrino or antineutrino is being formed with other leptons. Okay, so at least whenever you learn that, so that is what they are asking. They are asking that what reaction could take place, or what decay process could take place, or what could not take place. So we will learn minimum that. So this is pi minus. So it is forming mu minus, and if it is -1, now this particle must be neutral, which it happened to be. And I told you, whenever you will find it minus, so the same thing will appear here. Okay, means that is definitely not the minus sign, that is bar sign. Okay, but we are noticing it for the sake of remembering it. Okay, so whenever you see minus look here, then you will find it here. Okay, so whenever you see that, you will find the same pattern. So notice the pattern, it will be easy for you to remember. So even if I tell you, okay, let me hide it, let me totally cover it. If you know that, okay, this is the pion and pion is converting into muon, you should know it. Pion is converting into muon. Okay, then one neutrino will form, but what kind of neutrino? Anti-neutrino. Okay, so that is it. Now the same thing, pi plus. If it is pi plus, then to conserve the charge, here we will have mu plus, and then here we will have neutrino. So this is anti-neutrino of tau, and this is neutrino of tau. Now this is how it formed. Okay, it formed from pion. Now let us find how it decays or gets destroys. Because it is unstable, so it must decay. So you take one muon with minus sign, then it will convert into electron, which is stable. And I told you, if there is electron, so electron has sign charge minus. So here we will have anti electron, anti neutrino, and you will have muon neutrino. So know that if muon is decaying, then muon neutrino is also forming. Okay. So you need to know the pattern that with a lepton, this kind of similarity pattern you will always find. Okay, you practice it, you notice it in enough number of times, then you will automatically remember it. I recommend you at least practice this 3 to 4 times. Okay, and you are done. They are asking not much from particle physics. Now we have same thing for mu plus, which is converting into E plus, and then electron neutrino, and then muon antineutrino. That is it. Now we have the third lepton, that is tau lepton. So you combine two electrons, one with positive and one with negative charge, okay, to form tau plus and tau minus, and it happens at very high energy. Okay, when electron and these are at very high energy, you accelerate them to very high energy, then you collide them, then there will be chance that you find the tau lepton. That is what they are doing in the CERN or LHC, whatever you call it. Basically the particle colliders. Now let us follow the how they are decaying. This is how they formed. So take tau minus. So tau minus will automatically convert into what? Mu minus. And then for this minus, we know that this sign will appear. That means we have the muon antineutrino. And if here is antineutrino, then here we will have just neutrino. This is antineutrino. Then this is just neutrino. That is it. And now we have tau plus. So tau plus is converting into mu plus. And you should notice that how the charge is being conserved. Here we have -1, here we have -1, these two are neutral. So overall charge on left side is -1, overall charge on right side is -1, charge is conserved. Okay. So charge conservation is the basic necessity which is required to fulfill in all kind of process. All kind, whether it happens from strong or weak or electromagnetic, whatever, it will happen everywhere. But something will happen only in kind of strong or electromagnetic. For example, one such example is we have already learned it, that parity. Okay, we have done it already in the nuclear physics. That is, parity is violated in weak interaction. Violated in weak interaction means parity is applicable only in strong interaction. Okay, but charge conservation is applicable everywhere, whether weak or strong doesn't matter. So we'll see each and everything in pure detail so that you do not leave even a single question from particle physics. That is what we all should be confident of, because this game is also about confidence. Now, what happens? You again take tau minus. This time with the suitable energy, what will happen? It may also decay into a kaon. This is K meson. We have, and it is also called kaon. So let me tell you, we know that each and every particle is either lepton or hadron, and hadron is of two kind. One is meson and another is baryon. And baryon is of two kind. The first one is nucleons and the second one is hyperons. So you must remember this much. Okay, we have done the leptons classification and we are into details of the decay and the formation process. And for meson, we have three things. Basically, we know that it is pion, which the pi sign, then kaon with k sign, and then eta meson, eta meson with eta sign. That is it. Okay, so right now we know that kaon is being formed, and whenever you find that if they have written it, okay, this is going to k plus and some kind of neutrino, then you know it is wrong because neutrino is neutral particle. Neutrino is neutral. Then here it is minus, then here it is plus, then it is wrong because charge is not conserved. So they should be both the same. So that is why this is wrong. Okay. And so this is how you have learned minimum how charge is being conserved and how neutrino and anti-neutrino is being produced. Now let us learn about electron neutrino. That means till now we have learned the three basic things of lepton. I have told you that leptons you could remember with the mnemonic E, M and T. Okay. E is electron, M is muon, and T is tau lepton. And for these all things, we will have their neutrino particle as well. Electron neutrino, muon neutrino, and tau neutrino. So we have studied the first three. Now let us study the last three of the leptons. So electron neutrino. So you take one proton. So one proton, that means it will have positive charge. We know that. Okay. And it forms the neutron. So a neutron have neutral charge. Then that means the next particle will be obviously something with the positive charge to balance the charge, and then one neutrino of the electron. So you are seeing that electron is a kind of lepton which is always coming with its neutrino counterpart. Okay, so we have electron neutrino, electron neutrino. Okay, now the reverse could also happen. A neutron could form proton. So neutron is of zero charge, proton is of one charge. So to balance it out, we will have -1 here. Okay, so this is making the charge zero, and this is obviously the chargeless neutral particle. And I have told you that whenever you find E minus, then there will be anti-neutrino. And how could you do that? Just a desi way, you check this. Okay, so this is a kind of mnemonic only. There is no such concept. Okay. Now, what do we do? You take one electron neutrino and one neutron of the sufficient energy. You combine them, then you will find that you have got proton and electron. In simple manner, you can do the same thing with anti-neutrino. And when you took electron or neutrino, then you took neutron. And when you took electron anti-neutrino, then you will took proton. So you can see the oppositeness or symmetry kind of thing here. And earlier we have proton and electron, now we'll have neutron and positron. Okay, so this is how when you only focus on charge, it is very easy for you to remember. Okay, the first thing is that charge should always be conserved. Okay, always. Now we have muon neutrino as well. So you take muon neutrino and neutron, add them up. So you can find muon of negative charge plus proton. And you should know on the left hand side the charge is 0 for both the particle. So overall charge is 0. So on right side, hand side, it is overall -1, and for proton it is +1. So overall it is 0. So that is why uh, it is correct because charge is conserved. Now, a pion could also make muon and muon neutrino. So these are the reactions. And you need to practice them enough. I have told you minimum 3 to 4 times because these are the basic chunks which you must know. If you know the basic chunks, you will automatically do advanced chunks easily. In neutrinos are chargeless. We know that all the neutrinos, electron neutrino, muon neutrino, and tau neutrino, and their antiparticles, that is electron antineutrino, muon antineutrino, and tau antineutrino, they all are chargeless, but they do have masses. And this for this particular development, they have found it using the oscillation method. They showed that okay, these oscillates, and they won Nobel Prize for this. I think 4 to 5, no, in 2016 or 2015, if I'm not wrong. Just confirm it, okay? Just a general trivia for you. Now we are done with leptons, okay? Now move to hadrons, the second big classification of particles. So we know that hadrons are either mesons or baryons, and mesons are of bosonic category. So they have a spin nh bar, and these are fermionic category. So they have a spin on the odd multiple of that. Okay. So uh, let us first learn about mesons because these are simpler, and only three particles we have: pions, kaons, and eta mesons. Okay, and pions are also called pi mesons. These are called k mesons, and these are called eta mesons. Now, pions are of all the three charges: plus, minus, and neutral. So what will happen? Let me tell you. So pion will now let us move forward because these all things you need to remember. I have already done it. Okay, and these all are simpler. As you will move forward, as you will practice second time, third times, I am very sure it is very easy. So this is pion is moving into decaying into mu plus. Okay, charge is being conserved, plus sign both sides. This neutrino is neutral. Okay, and this muon could further decay into these three. Okay, we have done it already. So in that way, this is about pi plus, pi minus, and pi 0. Pi 0 is a neutral particle, so it is annihilating into just two photonic energy. Now, how they are formed? These are about all about decay, how they are decaying. Now, like let us know, two protons of a sufficient energy, when they meet, they form pi plus and this d. Now, let me only one thing for you. Right now, we don't know it. Okay, so we'll know it further. So just know that, just remember these all. And if you do well, you should know that this is charge 1, this is charge 1, and this is charge 1. So to conserve the spin, this is also charge 1. So that is what the Broder radio must have. Now you combine proton and neutron, so it will form a pion with negative charge and two protons. Okay, and again the charges are conserved. You should know that this is charge 1 and 0, and this is -1 and +1 and +1. So overall, left hand side you will have total charge 1, and right hand side you will have total charge 1. The same thing, you take the proton and treat that with sufficient energy, that is a photonic kind of particle or whatever you want to name that, and you will automatically get that it is making uh, muon with neutral charge and one proton. Okay, so you are simply getting your proton back, and you are just converting into energy into this part. Okay, so this is how the pions are being made. Now we have also weaker decays that happens, you know, even they are having low energy. Okay, or say that when they have low energy, they don't have enough kind of energy to hold them, so they decays. So pi plus is decaying into mu plus and giving the neutrino. Okay, muon neutrino. Pi minus is converting into mu minus and then giving muon antineutrino. I have again told you minus sign here and this bar sign here are similar, so remember it like that. Then pi plus minus is converting into pi 0 and then electron plus minus to conserve the charge and then electron neutrino and then pi minus is converting into electron and then electron antineutrino. Now let us move to the second part of the mesons, that is kaons or K mesons. We call it K mesons as well. Again the same thing. This is a pi minus and take one proton, they add up to the K 0 and this is lambda hyperon. What is it? This is lambda hyperon. I have again told you that this sign is of capital lambda. Okay, now take pi minus and add proton to it. With obviously there is a requirement of sufficient energy. Okay, then you will find neutron and K plus and K minus. These are kaons, but with a positive and negative charges. Similarly, you take pi plus and proton, then we'll have K plus and K0 antiparticle of K0. It is what? Antiparticle. Bar represents antiparticle generally. Antiparticle of K0 and then proton again. Okay. Now you could decay also K plus. So how you will decay? You take K plus and under some sufficient condition. What condition? That is not our job to know right now. Okay, we are not something into the particle acceleration department. We just are learning how the reactions or decay or production is happening and how the things are conserving. That is where the most of the questions are being formed. So K plus is moving into mu plus and then muon neutrino and then K plus can also go into the pi plus and pi 0. Okay, why can't it get pi plus and pi minus? Because charge is not conserved. On the left hand side you have charge plus 1, on the right hand side you will have 0. That is why next this can't happen, but this can happen. Now we have eta meson. So what you do, you take hydrogen and pi plus, combine them, you will get 2 proton and 1 eta meson. This is what? Eta meson, the third kind of meson. You take K minus and 1 proton, then you will find 1. This is, again try to remember, this is lambda. This is lambda hyperon. And let me tell you once again, and this lambda hyperon, this is eta meson. Let us know the classification once again, just so that you remember it. So particles are basically leptons or hadrons. Hadrons are basically mesons or baryons. And baryons are of two kinds. One is nucleon and another is hyperon. Nucleon and another is hyperon. We are studying mesons right now. Mesons were of three kinds. What? First one is pi meson or pion. Second one is K meson or K mesons or kaons, Kaons. And the third one is eta meson. I don't know why they don't call it etaons or whatever. I should have named it etaons. But obviously we are just aspirants. So now this is about production. They are being produced here. Now let us know about decay as well. So there is one eta meson. It is decaying into two equivalent energy, whatever the energy is. So right now I haven't told you the masses of each thing, because masses right now would have complicated. Our focus is just to know the classification. Okay, so we are knowing classification, we will know masses later on, and depending on the rest masses there will have the decay on what kind of energy it happens. It happens to get into finally. So the first thing is that a eta meson can completely disappear by just giving energy. This is nothing but energy. Also, eta meson can give us three neutral pions. Three neutral pions. and A times S1 can give us one plus pion, another minus pion, and one is neutral pion. And then again, what we will have? Plus pion, minus pion, and then just energy. In each and every case, the charge is being conserved. You could know that A times S1s are only having zero charges. Okay, we haven't found something with positive or negative for the A times S1. Okay, now let us move to the last classification of hadrons, that is baryons. We know baryons are what? Fermionic, and they have a multiple of spin in the multiple of h bar by 2. So we have nucleons and hyperons here. Nucleons, obviously we know, is neutron, proton, and their anti-particle. So we are done with nucleons with just that one neutron could get you one proton. And for charge conservation, if protein is being produced with charge plus 1, then the electron would be with minus 1. And then anti-neutrino, because we know that if here we have minus, then here we will have bar, that means anti-neutrino. So hyperons are basically unstable and they behaved in a strange way, that is they formed through strong force and decayed through weak interaction. That is the strangeness, and that is not the only strangeness. Okay, and for them we got clue about additional quantum number, which is strangeness. Okay, so let us know about the hyperon. It is called lambda hyperon. Okay, so you take one pion with minus charge, combine it with one proton, it will give you lambda hyperon, and kaon with zero charge. And mass of hyperon is, this is a wrong sign, this is the correct sign. Mass of hyperon is 1115.7 million electron volt. Okay, then this is how the lambda hyperon is formed. Now these all are about decays. So lambda hyperon may decay into proton, then pi minus, or neutron, then pi 0. Just for the sake of conservation of charge, charge is being conserved each and everywhere. Okay, then they can also move form the proton and electron as well, but when they form the electron, they will have its counterpart. Okay, that is electron anti-neutrino. And this can also decay into neutron and just gamma radiation energy, whatever you want to call. After lambda hyperon, we have sigma hyperon. And sigma hyperon, these all are the decays, that sigma plus will move into proton plus pi 0. Sigma plus could also move into neutron plus pi plus. Okay, just because they are conserving the charge. So you can see that if here it is 1, then here it would be 0 because it is plus. If here it is 0, then here it would be plus 1, and so on. So these all are pretty easy till now. Sigma plus would also give you a lambda hyperon, then E plus and electron neutrino. And E plus would also give you proton plus just energy. Okay, so there are various ways of decaying depending on what condition, microscopic condition is there, and that is what scientists are still studying, that in what condition what things are being produced, and this whole thing. Then let us do the same thing for E minus. So E minus is moving into decaying into N neutron plus pi minus and neutron plus electron, and then if there is electron, then there will be electron anti-neutrino. Notice that electron is always accompanied till now, whatever we have seen is with electron anti-neutrino. That is it. And neutral sigma hyperon is giving a one hyperon and one gamma ray. That is it. And we have these three, and they are anti-particles. And it goes unsaid, even if I don't tell you that okay, there is some anti-particle, then that doesn't mean anti-particle is not there. Anti-particle is always there. Now we have chi hyperon. Okay, this is chi sine, this is chi hyperon. You can read it as KIE or whatever you like, chi hyperon. So chi hyperon, chi minus is moving in, is decaying into sigma hyperon with neutral charge, and it is minus, then another will be pi minus. Similarly, you could see these all three. Okay, now there is no point in dictating each and everything. Let me tell you one very important observation till now, that chi plus has not yet been observed. Okay, so these all were about the chi minus. These are all about decaying of the chi 0. Okay, so they are decaying in such fashions, and one hyperon may create another hyperon, or they may also create um, meson, okay, and also leptons. Okay, so this is what happened. And in the last one we have omega hyperon. Omega hyperon is discovered from this reaction, that is, we have Ka minus plus proton gives omega minus, and then K plus K0, and charge is being conserved everywhere. Here we have charge -1 +1, that is overall 0. Here we have -1 +1 and then 0, overall 0. Then this is the decay scheme for omega minus. You just note it, and using these all chunks, we will learn that how UPSC is asking questions, which kind of interaction is possible, which kind is not possible. And this is all about basic one. We will move into the slightly advanced one as well in the next lecture. So let us meet in the second part.